We grow up hearing the name Alpha Centauri as if it were already half familiar, the first star system waiting just beyond the edge of our own. And that familiarity tricks us. It makes the nearest famous neighbour sound reachable, inspectable, almost simple. But when James Webb turned toward Alpha Centauri A, the nearest sun-like star, it did not find an easy target waiting in the dark. It found one of the hardest kinds of truth in astronomy, something close enough to matter deeply, bright enough to blind us, and quiet enough that a possible world could appear for a moment and then slip back into uncertainty. And if you enjoy this kind of slow journey through real science, stay with me. These are the stories that feel even larger when you let them unfold at their natural pace. Now, let's begin with the mistake almost all of us make. We hear that Alpha Centauri is only about 4.3 light-years away, and some part of the brain relaxes. Only, the word itself is the trap. 4.3 light-years sounds small because our minds were built for neighbourhoods and roads and coastlines, not for distance measured by light. In human terms, the next house is a short walk. In cosmic terms, the house next door is so far away that even light, the fastest thing the universe allows, needs more than 4 years to get there. A message sent tonight would not arrive before a child had time to grow older, before elections changed, before whole chapters of life quietly closed behind us. That is the first important shift in feeling. Alpha Centauri is close only by astronomical standards. It is not close in any human sense, and yet it is close enough to become intimate in a different way. Because once a star system is that near, the dream changes. It stops being a distant abstraction and starts to feel like local geography. Not home, exactly, but part of the same mental map. That is why Alpha Centauri has held such a strange place in the imagination for so long. It is not just another point of light, it is the nearest stellar system to our own. A triple system that includes Alpha Centauri A, Alpha Centauri B, and the smaller red star Proxima Centauri. Proxima already has confirmed planets, but the brighter pair, especially Alpha Centauri A, carries a different emotional charge. Alpha Centauri A is the nearest true sun-like star, not just nearby, familiar in the most dangerous way. Familiar enough that we instinctively want to know whether it has a system of worlds, whether somewhere around that star there is structure, warmth, motion, maybe even a planetary architecture that echoes something we know. And this is where the second misconception breaks apart. You might think the hard part is the distance. It is not. The hard part is seeing anything at all next to a star like that. Imagine trying to study a firefly circling a lighthouse from an absurd distance away. Not by noticing the lighthouse, which is easy, but by isolating the tiny moving ember near it. Now make the lighthouse many millions of times more overwhelming. Then add a second bright source nearby, because Alpha Centauri A lives in a binary partnership with Alpha Centauri B, and that companion complicates the scene. The problem is no longer simple remoteness. The problem is contrast, geometry, timing, optical brutality. A planet can be there and still vanish under glare. This matters because most exoplanets are not found by seeing them directly. Usually we detect them through their effects, a dip in starlight when they cross in front of their star, or a subtle wobble in the star itself. Those methods are powerful, and they have transformed our view of the galaxy. But they do not feel the same as direct imaging. Direct imaging is harsher and more intimate. You're not inferring a hidden object from a shadow or a tug. You're trying to isolate the world's own faint signal from the violence of the star beside it. That is why Webb's role in this story matters so much, not because it is a magic eye that simply reveals whatever it wants, but because it can look in a part of reality where planets do not have to shine like mirrors. They can glow with heat. Webb used its mid-infrared instrument, called MIRI, along with a coronagraph that suppresses some of the star's blinding light. The simplest analogy is putting your thumb over the sun, but that analogy is too kind. A real thumb blocks cleanly. A chronograph does not. It reduces glare, reshapes it, fights it, but never perfectly. The starlight still leaks and scatters and leaves behind a difficult landscape where faint things can hide. And yet the mid-infrared changes the game. Invisible light. A planet near a bright star is often just a weak little reflector, a dark bead trying to borrow enough light to be noticed. In the mid-infrared, a planet can betray itself through warmth, not with a dramatic blaze, but with something closer to body heat on a cosmic scale. That is the strange tenderness of this search. Webb was not looking for a glittering jewel beside Alpha Centauri A. It was looking for a warm ember in deep darkness. This becomes even more interesting around Alpha Centauri A because the star's habitable zone, the broad region where liquid water could in principle exist under the right conditions, sits at a separation that Webb can begin to probe in a meaningful way at this distance. That phrase, habitable zone, is one of the most misunderstood in astronomy. It does not mean inhabited, it does not mean Earth-like, it does not even mean safe. It means only that the temperature range may allow liquid water under the right atmospheric and planetary circumstances. A gas giant can pass through that zone and remain completely unsuitable for life as we know it, but its presence would still matter enormously, because giant planets shape systems, they sculpt orbits, they influence debris, they may host moons, and above all, they tell us that the system is not empty. So when Webb looked toward Alpha Centauri A, it was not merely checking a box on a list of nearby stars, it was testing whether the nearest solar twin could finally be forced into a more honest kind of visibility. Could we strip away enough glare, enough thermal confusion, enough instrumental residue to glimpse the architecture of another stellar neighbourhood? Could we do more than fantasize about Alpha Centauri? Could we begin to inspect it? That is the emotional engine under the entire story. Not aliens, not certainty, not the cheap thrill of announcing that everything we hoped for has already been found. The real tension is quieter than that. It is the fact that we now possess instruments delicate enough to look into the nearest sun-like system and reach the threshold where ambiguity itself becomes historic. Because once you get that close to the threshold, a single faint point of light can change the meaning of the whole sky. And in August of 2024, in Webb's mid-infrared view of Alpha Centauri A, that is exactly what seemed to happen. What Webb saw was not dramatic in the way people expect discoveries to look. There was no sweeping image, no clear outline of a world hanging beside its star. Instead, there was something far more fragile. A faint point of light, buried inside a difficult field of residual glare, appearing at a specific distance from Alpha Centauri A, not at the centre, not lost in the brightest part of the star's suppression zone, but offset, measurable, real enough to hold on to, and subtle enough to question immediately. That point would come to be called S1. To understand why that matters, we need to slow down and look at what a point of light actually means in this context. Because in everyday life, a point of light is trivial, a reflection, a distant car, a star in the sky. But here, the situation is inverted. The star itself is overwhelming. The entire image is dominated by something too bright to look at directly. And everything else, everything that might matter, is hidden in the leftover structure of that brightness. So S1 is not just a dot. It is a signal that survived a process designed to erase the star's glare without erasing everything else, and that alone makes it rare. The position matters just as much as the signal itself. As one appeared at about 1.5 arcseconds from Alpha Centauri A. That sounds abstract, but we can translate it. At the distance of Alpha Centauri, that angular separation corresponds to roughly 2 astronomical units, about twice the distance from Earth to the Sun. If you imagine our own solar system, it places the object somewhere between Mars and the asteroid belt, leaning toward the outer edge of that region. Not close to the star, not far away either, right in a zone where temperature, motion, and long-term stability begin to form something recognizable. And here's where the story tightens. Because at that distance from a sun-like star, the environment changes in a very specific way. The energy from the star is weaker than at Earth's orbit, but not by an extreme amount. The equilibrium temperature for a large object there could fall into a range where thermal emission in the mid-infrared becomes detectable. Not bright, not obvious, but just enough to glow faintly if your instrument is sensitive enough. Webb is sensitive enough. The signal at 15.5 microns matched something very particular. Not reflected light, not a hot object blazing like a star. Something cooler. Something with an effective temperature on the order of a few hundred Kelvin, roughly between 225 and 250 Kelvin, under the most straightforward interpretations, that is cold by human standards, but in planetary terms, it is exactly the kind of quiet warmth you expect from a giant planet sitting at a moderate distance from its star. So the first layer of interpretation emerges. If S1 is real, and if it is bound to Alpha Centauri A, then the simplest explanation is not a rocky Earth-like world. It is a gas giant, something roughly comparable in size to Jupiter, maybe slightly larger, with a mass somewhere in the broad range of tens to over 100 Earth masses, depending on how you model its atmosphere and heat emission. That might sound less exciting at first, but this is where perspective matters. A gas giant in that position would sit inside the star's habitable zone, not as a habitable object itself, but as a gravitational anchor, a presence, a sign that the system has structure, and if such a planet exists there, it raises quiet but powerful possibilities. Moons, orbital resonances, a history of formation that could include smaller worlds we have not yet seen. But before we move too far into implication, the discipline of the moment matters, because a single detection is not a confirmation, it is an event. Astronomy is full of events that dissolve under closer inspection, signals that turn out to be background stars, or galaxies, or artifacts of data processing, especially in a field this difficult, where the target sits so close to the limits of what an instrument can reliably separate from noise. So the immediate response is not celebration, it is elimination. Could S1 be a background object, something far behind Alpha Centauri, coincidentally aligned in the field of view? That is always a possibility. But the team working on the data examined that carefully. The brightness and spectral characteristics did not fit neatly with a distant galaxy or a typical background star at that wavelength and that position. Could it be a foreground object? Something closer to us, drifting through the line of sight? Again, possible in principle, but the probability is low, and the motion constraints begin to tighten once you consider the observational geometry. Could it be an artifact? A ghost of the instrument? A residual of imperfect subtraction? A pattern masquerading as a point source? This is perhaps the most serious concern, because coronagraphic imaging is inherently messy. The starlight does not disappear cleanly. It leaves structure, rings, speckles, patterns that can trick even experienced observers. And yet, S1 does not behave like a typical artifact. It appears with a consistency that suggests something more coherent, something localized. This is where the story begins to feel different, not because certainty has been reached, but because the usual easy explanations start to fall away. And when that happens, the mind naturally tries to stabilize the situation. It wants a second look. That is how science protects itself from its own excitement. You do not trust a single appearance. You return, you observe again under slightly different conditions. You try to see if the thing persists. Because a real planet does not simply vanish. Or at least, that is what intuition says. So Webb looked again, not immediately but months later in February and April of 2025. Enough time for a real object to have moved along its orbit, but not enough time for it to disappear entirely if it remained in a region of similar visibility. And this is where the story takes its quiet turn. When Webb returned, S1 was not there. At first glance, that feels like the simplest resolution. The signal was not real. The story collapses back into caution. Another near detection. Another lesson in how difficult this kind of work is. But that is not actually what the data suggests. Because absence is not the same as contradiction. To understand why, we have to step deeper into the geometry of the observation itself. The coronagraph does not create a uniform window around the star. It creates zones, regions where sensitivity is high, and regions where it drops sharply. There are blind spots, areas where the residual glare becomes too strong, where faint objects are effectively erased even if they are physically present. Now imagine a planet orbiting Alpha Centauri A with a period of just a few years, something on the order of 2 to 3 years. If the earlier estimates and potential connections hold, that means its position relative to the star changes noticeably over the span of months, not dramatically from one night to the next, but enough that over half a year, it could shift from a region of good visibility into one of those problematic zones, a target crossing into the blind spot of a lens. So the disappearance does not necessarily mean S1 ceased to exist. It may mean it moved. And suddenly, the story's no longer about a single detection. It becomes about timing, about orbital motion, about whether we happened to catch a world at the exact moment it emerged into a window where it could be seen, only for it to slip back behind the structure of glare when we looked again. This is where patience becomes part of the science. Because if that interpretation is correct, then S1 is not gone. It is simply hidden again, waiting for the geometry to align once more. And that possibility, quiet, unresolved, and grounded in real observational limits, is what keeps the entire story alive. And that is the part of the story that feels most human, because it mirrors a frustration we know in ordinary life. You catch sight of something at the edge of clarity, something important enough to stop you in place, and by the time you look again, the angle is changed. The thing has not necessarily gone away. Your access to it has. Astronomy at this level is full of that kind of tension. We like to imagine telescopes as clean, commanding instruments, eyes that simply open wider and wider until nature gives up its secrets. But real observation is closer to listening through walls. You work with leaks, with distortions, with brief alignments that may not return on your schedule. The more ambitious the search, the more patience begins to matter as much as power. That is especially true around Alpha Centauri A because the star is not merely bright. It is familiar bright, sun-like bright, the nearest place in the sky where the word solar starts to feel uncomfortable, because now it no longer belongs only to us. And once you start thinking that way, the entire challenge shifts. This is not just another exoplanet hunt somewhere in the deep, statistical ocean of the Milky Way. This is the attempt to inspect the nearest sun-like neighbourhood and ask whether there is actual architecture there, actual worlds, actual orbital paths, actual warmth moving around another star that resembles our own. That is why even ambiguity becomes intimate here. If S1 had appeared around a distant star hundreds of light years away, the scientific interest would still be real. But the emotional charge would be different. Distance can make even remarkable discoveries feel abstract. Alpha Centauri does the opposite. It drags abstraction back toward the body. It makes the mind compare. If our sun sits at the centre of one planetary household, then what is happening in the next one over? Is there a giant world moving through the broad temperate zone around Alpha Centauri A? Are there belts of dust? Are there hidden inner planets? Is the system sparse, crowded, stable, violent, quiet? These are no longer fantasy questions. They are measurement problems. And this is where the story begins to widen in a very important way, because SC1 did not appear in a vacuum of hope. It arrived in a system that had already been pressed on by other instruments, other teams, other attempts to peel glare away from the nearest bright stars. Years before Webb's detection, another intriguing signal had been reported using the Very Large Telescope's NEAR experiment, which searched around Alpha Centauri A in the thermal infrared from the ground. That earlier candidate was called C1. It was never confirmed as a planet. It remained suggestive, uncertain, controversial in the careful way frontier science often is, but it planted a seed. There might be something there, something warm enough and separated enough to briefly register if the observing strategy is good enough and the timing is favourable. Now, to be very disciplined about this, S1 and C1 are not proven to be the same object. That would be far too strong. The connection is conditional, yet it is not a random fantasy either. If the two signals are related, if they are different glimpses of the same orbiting body seen years apart, then a possible picture begins to form, a giant planet on an eccentric orbit, moving around Alpha Centauri A with a period of roughly a few years, sometimes appearing in a region where one instrument can catch it, sometimes disappearing back into observational difficulty. This is one of the strangest things about planets when you try to image them directly. In our minds, planets are stable, substantial, almost obvious. But in data like this, a planet can behave more like a rumour with gravity, not because it is unreal, but because the star dominates everything. The object itself may be enormous, larger than Earth by far, perhaps close to Jupiter in radius, and still present only as a whisper of heat. That matters because the whisper is physically meaningful. The mid-infrared flux Webb measured is not arbitrary. It points toward a cool giant planet interpretation, because giant planets radiate thermally in ways that rocky worlds of similar separation generally do not at the same level. A Jupiter-sized body with an effective temperature in the neighbourhood of 225 to 250 Kelvin would not look bright to the eye. If you floated near it, the scene would be dim, cold, subdued. But in the right infrared band, against cosmic darkness, it could stand out just enough to betray itself. This is a beautiful inversion of instinct. We often imagine that seeing farther into the universe means seeing brighter, sharper, more spectacular things. Sometimes it means the opposite. Sometimes progress is the ability to notice colder things, quieter things, things that barely separate themselves from the background at all. And that is exactly why Webb's use of MIRI is so important here. Mid-infrared observation allows a different kind of honesty. Instead of asking whether a planet reflects enough starlight to be noticed, we ask whether it has enough warmth to register on its own terms, not a shining bead beside a lamp, but a warm body in the dark. That distinction becomes even more powerful when we remember what kind of star Alpha Centauri A is. If Proxima's planets are emotionally interesting because Proxima is the nearest star of all, Alpha Centauri A is interesting in a more unsettling way. It is the nearest place where the host star resembles our Sun, enough to invite comparison without much effort. The language of solar neighbourhood starts to stop being metaphorical. The nearest solar twin is no longer just a direction in science fiction. It is a system under observational pressure. And our intuition still keeps failing us here, because closeness should have made things easier. That is what the brain expects. A nearby city is easier to map than one on another continent. A nearby tree is easier to inspect than a mountain on the horizon. But stars punish that kind of intuition. A closer star can be harder in certain ways precisely because it is brighter, and because the planet-star contrast problem remains vicious. It is like trying to notice a warm ember beside a floodlight. Moving the whole scene somewhat closer helps, but it does not cancel the floodlight. There is another layer to this as well, one that rarely gets the same attention as the planet candidate itself, even though it may prove just as consequential in the long run. Webb's observations around Alpha Centauri A also placed extremely deep limits on exozodiacal dust. That phrase can sound technical, but the idea is simple. Every planetary system can contain dust, fine particles from collisions, comets, debris, slow-grinding destruction. Around a star, that dust glows, not dramatically, not like a nebula, but as a diffuse haze. If there is too much of it, it becomes a problem. It fills the system with a kind of luminous clutter, a faint glow spread across space that can hide planets or confuse the view. Think of sunlight pouring into a room thick with suspended dust. You can still see the room, but the air itself becomes part of the visual problem. Around Alpha Centauri A, Webb found something very important. That haze appears to be faint, remarkably faint, only a few times brighter than the zodiacal dust in our own system, by some of the deepest limits ever achieved for any stellar system. That sounds modest, but its implications are enormous. It means Alpha Centauri A may be relatively clean, at least in the regions Webb could constrain. A system where future direct imaging efforts are not fighting a bright fog of debris on top of stellar glare. In other words, the nearest Sun-like star may not only contain a plausible giant planet candidate, it may also be one of the best nearby environments in which to keep looking. That combination is what gives the story its weight. A possible world, seen in thermal emission, near the habitable zone, around the closest Sun-like star, in a system that may be unusually favourable for further searches. None of that adds up to certainty, but it does add up to something else. A frontier that has begun to answer back. And once that happens, once the nearest familiar star starts producing even tentative hints of hidden structure, it changes the way you look at the night sky. Alpha Centauri stops being a name that lives mostly in imagination. It starts becoming a place with constraints, possibilities, blind spots, and timing windows, something more like a real neighbourhood that we have only just begun to map. Which raises a deeper question, and a more difficult one. If S1 is real, what kind of planetary system would allow such a body to live there at all? Because the moment we allow that possibility, even cautiously, we're no longer asking whether a planet might exist. We're asking how an entire system organizes itself around a star that is both familiar and not ours. Alpha Centauri A is not alone. It lives in a binary partnership with Alpha Centauri B, and that changes everything. The two stars orbit each other over decades, moving in a slow gravitational dance that reshapes the environment around them. At times they are relatively close, at times more distant, but always present in each other's sky. If you stood on a world orbiting Alpha Centauri A, Alpha Centauri B would not be a distant pinprick. It would be a bright, shifting companion star, altering the background light, tugging gently but persistently on every orbiting body. That second star is not strong enough to tear stable planetary orbits apart close to Alpha Centauri A, but it does complicate the long-term structure. It introduces subtle gravitational influences, especially over millions of years. It can stir debris, reshape outer regions, and influence how planets settle into their paths. So when we imagine a giant planet at roughly 2 astronomical units, we are not placing it in a quiet, isolated system like ours. We are placing it in a dynamic environment where 2 stars have been negotiating space for billions of years. And yet, stability is still possible. In fact, simulations suggest that planets can exist in relatively stable orbits around each individual star, as long as they remain close enough to their host and far enough from the influence of the companion. The region around Alpha Centauri A where S1 appeared falls within that stable zone. Not comfortably distant, but well within the boundary where a planet could persist over long timescales. So now the picture becomes more grounded, a sun-like star, a possible giant planet orbiting at a moderate distance, a second star shaping the outer architecture but not destroying it. This is not chaos, it is structure under tension. And structure matters, because planets do not form randomly. They emerge from disks of gas and dust, from collisions and accretion, from processes that leave signatures behind. If a giant planet exists there, it implies a past, a history of formation where enough material gathered, enough time passed, and enough stability remained for something large to grow. That alone would already shift our understanding of the nearest solar twin. Because for years, Alpha Centauri A and B have been frustratingly quiet in terms of confirmed planets. Proxima Centauri, the smaller companion star, revealed its planets relatively quickly, but the brighter pair resisted clear detection. It created an odd imbalance. The nearest system to us clearly hosted planets, but not around the stars that most closely resemble our Sun. This led to a quiet question in the background of astronomy. Was something about the Alpha Centauri AB system suppressing planet formation? Was the binary interaction too disruptive in its early history? Or were the planets simply there, hidden behind the limits of our methods? Swan leans toward the second answer, not conclusively, but suggestively. It hints that the system may not be empty at all, but merely difficult to read. And that difficulty becomes easier to understand the more closely we look at the physics of detection itself, because even with Webb, even with mid-infrared sensitivity, we are still dealing with extreme contrast. The star dominates the field. The coronagraph reduces that dominance but leaves behind patterns. Those patterns are not noise in the casual sense. They are structured remnants of light, shaped by optics, by diffraction, by the physical design of the instrument. Inside those patterns, a real object must separate itself not only from darkness, but from false structure that can imitate it. So when S1 appears, it is not emerging from emptiness, it is emerging from complexity. And that means every interpretation must pass through layers of caution. You do not simply accept the signal, you interrogate it. You ask whether it behaves like something physical or something artificial. One of the most important distinctions is coherence. Real objects tend to produce consistent signals across different processing approaches. Artifacts often shift or dissolve when the data is handled differently. S1 shows a level of persistence that resists simple dismissal. Not absolute proof, but enough to keep it in play. Another layer comes from brightness and temperature. The signal corresponds to a level of thermal emission that fits within a narrow range of plausible planetary models. Too bright, and it would suggest something else entirely. Too faint, and it would sink below detection. It sits in a space that is physically reasonable for a giant planet under the right conditions. But then comes the tension again, because if this is a planet, why didn't we see it again? And here, timing becomes everything. A planet at roughly 2 astronomical units around a Sun-like star would orbit with a period on the order of a few years. That means its position changes significantly over time, but not instantly. Over several months, it can move from one side of its orbit toward another, altering its projected separation from the star as seen from Earth. Now layer that motion onto the structure of the coronagraphic field. There are regions where detection is easier, and regions where it becomes nearly impossible. If the planet crosses from one into the other, its visibility can change dramatically without the planet itself changing in any fundamental way. So the disappearance of S1 does not behave like a contradiction. It behaves like a clue. It suggests motion. It suggests that what we saw was not a static artifact, but something that occupied a particular place at a particular time, then moved into a region where our sensitivity dropped. And this is where the story quietly deepens again, because now we are not just asking whether something exists, we are asking where it went. If S1 follows an orbit that brings it back into a favourable viewing region, then future observations may recover it, not as a surprise, but as a confirmation of motion, a pattern emerging across time rather than a single moment. That is how planets become real in this domain, not through one image, but through consistency across multiple passes, each one constrained by physics, by geometry, by prediction. And yet, even without that confirmation, something has already shifted. Because Webb did not only look for planets, it also measured the environment in which those planets would exist. The limits it placed on exozodiacal dust are not just a side note, they are part of the same story. A cleaner system means fewer false signals, fewer confusing glows, fewer obstacles between us and whatever may be orbiting there. It means that the difficulty we're facing is not compounded by a thick haze of debris. It means that when we do see something, the chances that it is meaningful increase. So now we have a system that is both challenging and promising. A place where glare remains a brutal problem, but where the surrounding environment may be more favourable than expected. A place where a possible giant planet has appeared once, in exactly the kind of region we hope to probe, then slipped away in a way that fits orbital motion rather than immediate dismissal. And this brings us back to the emotional core of the entire story. Alpha Centauri is no longer just a destination. It is becoming a place with behaviour, a place where timing matters, a place where geometry matters, a place where something may already be moving, just beyond our current ability to hold it in view. And that changes the relationship entirely. Because once a star system begins to show behaviour, even tentative behaviour, it stops feeling like scenery. It becomes local weather in the deeper sense of the word, not weather of clouds and wind, but of motion, architecture, hidden bodies, changing alignments. And the human mind responds to that almost immediately. We are built to care more about moving things than static ones. A distant mountain is impressive. A light in the mountain that appears once and then vanishes is unforgettable. That is the emotional logic under S1. If all Webb had done was tell us that Alpha Centauri A remains difficult to image, the result would still matter scientifically, but it would not rearrange the imagination. Difficulty alone does not do that. What changes everything is the possibility that the nearest Sun-like star may already have given us a thermal glimpse of a giant world in motion. Not a fantasy, not a headline inflated into nonsense, a physically plausible, observationally grounded, still unconfirmed signal that seems to belong to a real system rather than an empty one. And once you allow that possibility into the room, another thought begins to form. If a gas giant can exist there, what else might be arranged around it? We have to be careful here, because this is where excitement can become dishonest. A giant planet in the habitable zone does not mean a habitable planet has been found. It does not mean life. It does not mean Earth too. It does not even mean that smaller rocky worlds are present. But giant planets are rarely meaningless. In any planetary system, large bodies act like organisers and disturbers at the same time. They shape gravitational traffic. They influence where debris survives, where smaller objects migrate, where impacts become more or less likely. They can help clear regions. They can destabilize others. They can shepherd material into resonances that persist for enormous spans of time. So a giant planet is not just a planet, it is a statement about the system. In our own solar system, Jupiter is not merely one world among many. It is part of the reason the entire system looks the way it does. It influenced the history of the asteroid belt, altered the pathways of comets, and likely played a role in how the inner planets evolved. If Alpha Centauri A has an analogous body, not identical but comparable in dynamical importance, then the nearest solar twin may have been shaping its own local architecture all along, while we stared at the star itself and saw almost nothing. That is one of the quieter humiliations of astronomy. The universe can hold large, consequential things directly in front of us for ages, and all it takes to hide them is brightness. You can feel that intuitively if you have ever tried to see something small near a street lamp at night. The object is not distant. It is not even especially dim in absolute terms. The problem is contrast. Your eye is overwhelmed. Its whole operating range gets distorted by the nearby brightness. Webb, for all its power, still faces versions of that same problem. A nearby star can saturate the scene with difficulty. And Alpha Centauri A has a second layer of complication that is easy to forget because the main drama focuses so tightly on one star. Alpha Centauri B is not just a footnote. It is another bright stellar presence in the same overall system. Its gravity matters over long timescales, and its light matters in observational strategy. You're not imaging a world in a perfectly clean laboratory. You're trying to isolate one faint thermal source in a neighbourhood where two luminous suns are part of the broader geometry. This is why the phrase nearest place can be so misleading. Nearness does not mean simplicity. In many ways it means the opposite. The system is close enough to reward extraordinary effort, but still remote enough that every effort happens through filters, through optics, through orbital projection, through residual glare, through time windows that do not care when you happen to be ready. And then there is the orbit itself. If S1 and the earlier C1 signal are related, and that remains a very careful if, then the possible orbit may be eccentric, not a neat, almost circular path like the simple textbook diagrams people often carry in their minds, but an elongated one, a more dramatic route around the star, changing the projected separation and brightness conditions over time. That would help explain why the object can appear in one epoch and vanish in another. It would also make the timing of future observations more important than ever. Because once you suspect an eccentric orbit, prediction becomes delicate. The world may not return to a favourable viewing position in the way a simple circular model would suggest. It may emerge unexpectedly, linger briefly, then move back into a region where the star's suppressed but still overwhelming light swallows it again. A boat between waves. That analogy is imperfect, but emotionally useful. You're not waiting for the boat to come into existence. You're waiting for the sea to permit a line of sight. This changes the nature of the suspense. It is no longer the loud, artificial suspense of did they find a planet or not. It becomes a more realistic, more absorbing kind of suspense. Is the system behaving the way a planet-bearing interpretation predicts? Are the non-detections consistent with motion through poor sensitivity regions? Can the earlier and later glimpses be made to fit one coherent physical story? These are slow questions. They do not explode. They accumulate. And that slow accumulation is part of what makes this story so powerful for a tired mind listening at night, because it reflects how reality often reveals itself, not by shouting, but by refusing to become simpler. There is another emotional layer here that almost never gets stated plainly, though it sits under the surface of every serious discussion about Alpha Centauri. For generations, this system has occupied a double role in human culture. It is a real astronomical target, and it is also one of the oldest destinations in our fictional imagination. When writers wanted a nearby star that felt plausible, reachable in some remote future, meaningful as a first crossing, Alpha Centauri was often waiting for them. It became a placeholder for the next great outward step. But fiction has a way of smoothing things. It turns a star system into a destination marker. It strips away glare, blind spots, data reduction, coronagraph design, exozodiacal dust, background confusion, orbital timing. The real system is harder and more intimate than that. It is not a clean promise hanging in the sky. It is a difficult field of light where any actual discovery has to be wrestled from physics. And somehow that makes it more moving, not less. Because the universe is not giving us Alpha Centauri as a mythic reward. It is giving it to us as an observational frontier, piece by piece, constraint by constraint, signal by signal, first Proxima's planets, then limits on dust around Alpha Centauri A, then a possible thermal point source in the habitable zone region, then silence on the next pass. Not empty silence, but structured silence that may itself be part of the same story. That is the shift from fantasy destination to measured reality. The difference matters. A fantasy destination stays safely vague. A measured reality begins to develop texture. Distances become specific. Temperatures become specific. Orbits become specific. Even uncertainty becomes specific. And once that happens, the emotional relationship deepens. We're no longer projecting whatever we want onto the nearest sun-like star. We are beginning to learn what kind of place it may actually be. A place with a relatively clean dust environment. A place where a giant world may be moving through the broad temperate region around its star. A place where a second sun alters the wider architecture. A place still mostly hidden, but not completely. That last phrase may be the most important of all, not completely. Because for most of human history, every star beyond the sun was essentially featureless. Beautiful, yes, meaningful, sometimes, but featureless. Even the nearest ones were points. The imagination could build worlds around them, but observation could not. Now that boundary has started to crack, not everywhere equally, not in one dramatic leap, but in enough places that the old sky is gone. We live in a time when nearby stars are beginning to acquire interiors in the mind. Not literal interiors, but systems, structure, contents. And Alpha Centauri A may be one of the most consequential examples of that change, precisely because it sits so close to us in both distance and emotion. Which means the real shock in the title is not that Webb saw something impossible. It is that the thing it may have seen was so physically ordinary in one sense. A giant planet, warm with faint thermal emission, orbiting another star, and so emotionally destabilizing in another. Because ordinary planetary architecture, if it exists around the nearest solar twin, would make the universe feel less empty in the most local way imaginable. Not everywhere, right next door. And once that thought settles in, another one follows naturally. If the nearest sun-like system truly contains a giant planet in that region, then what does nearby reality even mean anymore? Because nearby reality used to mean the Moon, then Mars, then perhaps the outer planets if you were feeling generous with imagination. Even the nearest stars belong to another category entirely. Less like places and more like symbols. They were destinations in diagrams, not environments. But the moment a star begins to yield signs of planetary structure, that category starts to dissolve. The star stops being a point and becomes a system, a neighborhood, not reachable, not familiar in any ordinary sense but no longer abstract. This is why the Alpha Centauri story lands so differently from many exoplanet stories. Most exoplanets live at emotional arm's length. We can admire them, study them, even become attached to them in a scientific way, but they remain part of a vast census. They are entries in a swelling archive of worlds. Alpha Centauri A is not like that. Its importance is not only what it might contain, it is where it sits in our mental map. The nearest sun-like star is the first place outside our own system where the architecture of another solar-style neighborhood could begin to feel uncomfortably real. And that phrase matters. Solar-style neighborhood. Not identical to ours, not a mirror, but the kind of place where our comparisons become difficult to resist. A giant planet at around 2 astronomical units from a sun-like star immediately invites those comparisons. You start translating without meaning to. Earth is at 1 astronomical unit from the Sun. Mars is farther out. Then the asteroid belt, then Jupiter. A body orbiting at roughly 2 astronomical units around Alpha Centauri A would sit in a region that feels neither inner nor outer in the dramatic sense. It would belong to the middle distances, where the warmth of the star still matters, where orbital periods are short enough to feel active, where a system's large-scale structure starts to become visible through motion. And that is important because motion is what turns speculation into reality. If the candidate is real, it is not a static ornament hanging beside the star. It is a moving mass tracing a path through space-time, responding to the gravity of Alpha Centauri A, shaped over time by the broader binary environment, perhaps affecting smaller bodies we have not yet seen. It has seasons of visibility and invisibility not because it chooses to hide, but because our instruments carve the sky into zones of access. This can be hard to hold in the mind because our visual intuition expects the sky to be straightforward. We think of looking as passive. You point, you collect light, you see what is there. But direct imaging near a bright star is not passive, it is adversarial. You are fighting the star to earn every faint photon from anything nearby. You are suppressing light, subtracting patterns, rejecting false positives, testing whether the shape in front of you is nature or residue. Even then, you do not get to keep the object unless the geometry is kind enough to let it remain visible. That is the deeper reason the non-detections in 2025 matter so much. Not because they invalidate the earlier signal, but because they force the story into the time domain. A one-time detection can always feel precarious. A disappearance that fits a plausible orbital explanation begins to act like a form of indirect evidence. Not proof, never that, but a structure of behavior that points away from randomness. And randomness is the enemy here. The easiest way to dismiss a faint candidate is to say it was chance alignment, chance artifact, chance overinterpretation. But the more the pieces start to fit a dynamical picture, the harder chance becomes to sustain as the comfortable answer. There is a quiet elegance in that. The candidate does not become stronger by staying still. It becomes stronger by participating in a coherent story about where it could move and why that movement would alter our ability to see it. This is one of the reasons astronomers care so deeply about repeated observations even when they return nothing. A non-detection is not empty. It changes the shape of what is possible. It narrows orbits, tests brightness assumptions, pressures alternative explanations. In ordinary language, "We looked and didn't see it" sounds like failure. In frontier observation, it can be part of the same evidence stream. That patience is difficult for the public imagination because public imagination prefers decisive moments. Discovery, confirmation, rejection. The real work is usually slower than that. A signal appears, models are tested, follow-ups complicate rather than simplify. The object moves from maybe imagined to maybe physical to maybe orbiting to maybe this specific kind of planet. Each step feels incomplete, and yet each step matters. In a strange way, that incompleteness is one of the most honest emotional experiences science can offer. It lets us feel reality while it is still being resolved, not packaged afterward into a neat ending, but encountered in the middle, when evidence is strong enough to matter and incomplete enough to remain alive. Alpha Centauri A is giving us exactly that kind of experience. And the more you sit with it, the more extraordinary the observational feat itself becomes. We are on one planet around one ordinary star, and we have built an instrument capable of detecting a faint thermal signal from a possible giant world around the nearest solar twin. Even if S1 were ultimately to turn out not to be a planet, that sentence would still remain astonishing. It tells you something about what our species can now do. Not in the triumphant sense, in the careful sense, in the sense that we have learned how to look with enough sensitivity that ambiguity itself can occur at planetary scale around another star. That is a profound threshold. For most of history, nearby stars were decorative in the strictest sense. They decorated the night, they guided navigation, inspired myth, and anchored calendars, but they did not yield local detail. Then came spectroscopy, and stars began to acquire chemistry, then precision measurement, and they acquired motion, then exoplanet methods, and stars began to acquire hidden companions. Now, with direct imaging and thermal sensitivity reaching systems this close, the nearest stars begin to acquire atmosphere in the mind. Not literal atmospheres first, but presence, particularity, a sense that each point may enclose its own layered reality. This is why the exozodiacal dust result matters emotionally as well as scientifically. A relatively clean environment around Alpha Centauri A means we're not staring through a glowing fog so bright that it overwhelms any future search. It means the system may be unusually favourable for continued attempts. There is space, observationally speaking, for more of the architecture to emerge. Imagine standing in a dim room with a bright lamp shining through airborne dust. If the room is thick with particles, every beam becomes muddied, shapes disappear into haze. If the room is relatively clear, the task remains difficult, but not hopeless. The contours can begin to separate. That is what Webb has done for Alpha Centauri A. It has not unveiled the whole room. It has shown that the air may be cleaner than feared. And that reorients the future, because this story is no longer only about what Webb may have seen once. It is about whether we have finally reached the era in which the nearest Sun-like system can be mapped in stages rather than imagined in generalities. That is a major emotional transition. We have dreamed about Alpha Centauri for so long that dreaming about it felt almost like a permanent state. Fiction could send ships there. Philosophy could project meanings onto it. Popular science could mention it as the inevitable next frontier. But none of that was the same as measurement. Measurement has a colder touch. It strips fantasy away and gives you constraints instead. Distances, temperatures, possible masses, dust limits, projected separations, missing follow-ups, blind spots. And somehow, those constraints make the place feel more alive. Because fantasy can promise anything. Reality offers resistance. When a place resists you, when it makes you work to know it, when it withholds itself except in brief, honest glimpses, that is when it begins to feel real. So Alpha Centauri A is crossing a line in our imagination not by becoming easy, but by becoming stubborn in a scientifically legible way. A possible world appears in August 2024. Follow-up observations in early 2025 do not recover it. The most interesting explanation is not collapse, but motion through an unfavourable region. The dust environment seems unusually clean. Earlier hints from ground-based work may or may not connect. The system remains unresolved, but no longer blank. And once blankness is gone, the sky changes with it. Because now the question is not whether the nearest solar twin is worth looking at. The question is how many secrets can remain hidden in a system that close once we have truly begun looking this carefully. And that question carries a strange kind of quiet pressure, because it forces us to reconsider something we thought we understood long ago. We assumed that if something important existed around the nearest sun-like star, we would have seen it by now. That assumption felt reasonable. Alpha Centauri is bright, prominent, and constantly observed. It has been part of human awareness for centuries. Modern astronomy has studied it across wavelengths, across decades, with increasingly sophisticated tools. It feels like a place that should already be known. But that feeling is rooted in the wrong metric. We tend to measure knowledge by attention. If we have looked at something often enough, we assume we understand it. The universe does not work that way. It is not how long you look, it is how you look. And only recently have we been able to look in a way that even gives a world like CES1 a chance to reveal itself. Direct imaging at this level is not just another observational technique added to a list. It represents a shift in what counts as visible. Before this, planets near bright stars were mostly hidden, unless they happened to transit or tug strongly enough to betray themselves. That meant entire classes of systems could remain effectively invisible, even if they were right next door in cosmic terms. Alpha Centauri sits exactly in that gap. Too bright for easy imaging, too geometrically inconvenient for consistent transit detection, complex because of its binary companion, close enough that we care deeply, but structured in a way that resists simple methods. So for a long time it looked quiet. Now we are beginning to understand that quiet may not have meant empty, it may have meant hidden. And once that idea settles, it changes how you interpret every piece of evidence, including the parts that seem frustrating at first. The single detection, the non-detections, the clean dust environment, the earlier hints from different instruments. These are no longer disconnected fragments. They start to feel like different angles on the same difficult reality. A reality where seeing is conditional. That word matters more than it seems. Seeing is conditional on wavelength, conditional on instrument design, conditional on the precise configuration of starlight suppression, conditional on orbital phase, conditional on how well we can model and subtract the star's remaining glare, conditional on whether the object sits just outside or just inside a sensitivity boundary at the moment we look. That last condition is especially important, because it brings the entire story back into time. Not abstract time, but the kind that moves quietly through months and years. A planet orbiting Alpha Centauri. A does not care when we schedule observations. It follows its path regardless, from our perspective. That path sometimes aligns with visibility, sometimes not. So the act of discovery becomes a kind of synchronization problem. You're not just looking hard enough, you're trying to look at the right moment. And that introduces something almost unfamiliar into modern astronomy: the need to wait in a very specific way. Not waiting because we lack capability, but waiting because reality itself has rhythms we must match. If S1 is a real planet on a roughly 2 to 3 year orbit, then there will be times when it re-emerges into a region where Webb or future instruments can see it again. Those windows may be narrow, they may not arrive when it is convenient, but they will come if the interpretation is correct. So now the story extends forward. The August 2024 detection is no longer just an isolated event. It becomes a reference point, a marker in the orbit. If the orbit exists, the early 2025 non-detections become constraints, and the next observations, whenever they occur, will not be blind. They will be guided by expectation. That is how a candidate turns into a testable hypothesis. And that shift, from surprise to prediction, is one of the most important transitions in science. It means we are no longer reacting to what the universe gives us. We are beginning to anticipate what it should give us next, if our understanding is correct. That anticipation carries its own kind of tension, not loud, not urgent, but persistent. Because if the object returns where and when the models suggest, something solid begins to form, not certainty, but structure, a repeated presence, a trajectory, a consistency that randomness struggles to imitate. But if it does not return, if repeated observations continue to miss it even in regions where it should be detectable, then the interpretation shifts again. The system becomes more complex, not less. Perhaps the orbit is different. Perhaps the brightness assumptions are wrong. Perhaps the signal was something we still do not fully understand. Either way, the story deepens. There is no version of this where we go back to not caring. That is the quiet point where Alpha Centauri A has now arrived. It has crossed from being a well-known star to being an active investigative site, a place where each observation matters, where each constraint reshapes the possible map of the system. And if you step back for a moment, the scale of that shift is extraordinary. For most of human history, the nearest Sun-like star was a point of light we could not meaningfully interrogate. Now it is a place where we are debating the orbit of a possible giant planet, the brightness of dust at levels comparable to our own system, the sensitivity limits of mid-infrared imaging, and the geometry of detection windows measured in fractions of an arcsecond. That is a different relationship entirely. And it brings us back, in a very quiet way, to the title of this story. Because the phrase "what it saw shocked scientists" can easily be misunderstood as something dramatic, something explosive, something that breaks the rules of nature. But the real weight of what Webb saw is almost the opposite of that. It did not break physics. It did not reveal something impossible. It revealed something plausible, and that is more destabilizing than it sounds. Because plausibility at this distance means proximity. It means that the nearest Sun-like system may already be giving us direct, if incomplete, evidence of planetary structure, not inferred through indirect methods alone, but glimpsed in its own faint thermal signature. That is a different kind of closeness. Not the closeness of travel, but the closeness of knowledge. You cannot go there, not in any practical sense, not with anything we currently possess or are likely to possess in the near future. But you can begin to know what is there in a way that was impossible before. You can begin to track motion, constrain mass, estimate temperature, map dust, predict future visibility. And once that kind of knowing begins, distance changes meaning. 4.3 light-years is still immense. It still represents a separation that dwarfs human experience. But it is no longer empty space in the mind. It is filled with a system that may contain structure we can begin to describe. That is the subtle shock. Not that the universe surprised us with something exotic, but that it allowed something familiar, planetary structure around a sun-like star to emerge so close to us, hidden until now by the limitations of our own sight. And if that is happening at Alpha Centauri, the nearest solar twin, then the next realization becomes unavoidable. This is not the edge of what we will see. It is the beginning of how we will see nearby systems from now on. It is the beginning of a new kind of intimacy with the sky. For a long time, astronomy advanced by making the universe larger. We learned that stars were not lights attached to a dome, but suns scattered across a galaxy. Then we learned that our galaxy was one among many. Every major step seemed to push reality farther away, farther beyond scale, farther beyond the range where the human mind can comfortably hold it. And that expansion was real. But there is another kind of progress, quieter and perhaps more unsettling, not making the universe bigger, but making it more local. That is what happens when nearby stars stop being abstract and start acquiring contents. A star with contents is different from a star with a name. A named star can still remain symbolic. It can live mostly in story, mostly in culture, mostly in aspiration. A star with contents enters a different category. It becomes a system with weathered facts attached to it, possible planets, measured dust, orbital models, detection thresholds, gaps in visibility. It begins to feel less like mythology and more like geography. Alpha Centauri may be crossing that line right now, and the strange part is that the crossing happens not through certainty, but through sustained ambiguity. That sounds backward at first. We assume certainty is what makes a place real, but often, in science, the first sign that a place is becoming real is that its uncertainty becomes sharply detailed. Not vague uncertainty, not ignorance in the broad sense, specific uncertainty, the kind you can draw around, the kind that has temperatures, separations, orbital possibilities, rejected alternatives, and scheduled future tests. This one lives inside that kind of uncertainty. If it were just an unexplained glow, the story would be weak. If it were already confirmed beyond doubt, the emotional shape would be cleaner but perhaps less revealing. What gives this moment its particular power is that we are watching the nearest sun-like system become legible in real time. And legibility arrives first as contested detail. Something is there, or seems to be there. It was seen once in a way that fits a giant planet interpretation. It was not recovered later, but the failure to recover it may itself fit the motion expected of a planet. The surrounding dust appears faint enough that future searches have real promise. The earlier C1 signal may connect, though that remains unresolved. Every piece resists simplification, but together they form a pressure pattern. That pattern is what matters. Because the history of exoplanets has already taught us something profound, the galaxy does not hide planets because they are rare. It hides them because seeing them is hard. Once our methods improve, worlds begin appearing everywhere. Around red dwarfs, around sun-like stars, around stars with tightly packed systems, hot giants, super-Earths, mini-Neptunes, strange resonant chains, again and again. The lesson has been the same. The silence was partly ours, a limitation of technique mistaken for a limitation of reality. Alpha Centauri may be teaching us the same lesson under harsher conditions, and if that is true, then the system's resistance becomes almost poetic in the most grounded possible way. The nearest sun-like star did not turn out to be empty. It turned out to be difficult. That distinction changes the emotional temperature of the story. An empty system would close imagination down. A difficult system does the opposite. It sharpens it, disciplines it, keeps it awake. Because difficulty implies hidden structure, not guaranteed structure, but the kind of field where discoveries can still be waiting just behind the threshold of present capability. There is a deeper human point here as well. We often imagine knowledge as illumination, as if the goal is simply to flood darkness with enough light that everything becomes visible at once. But many of the most consequential forms of knowledge arrive differently. They arrive by subtraction, by suppressing glare, by learning what not to trust, by making a bright thing less overwhelming so that a faint thing can finally exist in view. That is exactly what coronography is. A disciplined refusal to let the star dominate every answer. The image of placing a thumb over the sun is simple, almost childlike, but it points towards something profound. We are learning to hide brightness in order to discover reality. We are learning that the things that most command attention are not always the things that matter most. A star blazes so strongly that it can make its own system disappear. To know the neighborhood, we must first quiet the center. That is a beautiful reversal, and it is one reason Webb's role in this story matters beyond the specifics of Alpha Centauri. Webb is not just a telescope collecting more photons. It represents a new threshold in how finely we can manage contrast, wavelength, and sensitivity together. Its mid-infrared capability is especially powerful because it lets us search for warmth rather than glitter. That difference may sound technical, but emotionally it is enormous. Glitter belongs to surfaces, warmth belongs to bodies. A planet seen in reflected light feels like an object borrowing the star's radiance. A planet seen in thermal emission feels more self-possessed, more physically present. It is not merely catching light, it is radiating the quiet consequence of its own temperature into space. That is what makes S1 feel so hauntingly plausible. If it is real, we are not seeing a bright bead near Alpha Centauri A. We are sensing the faint heat of a large world moving around the nearest solar twin. And that brings us to one of the most interesting misconceptions embedded in the phrase habitable zone. The public imagination hears those words and immediately begins to populate the scene with oceans, continents, and atmospheric blue. But the habitable zone is not a promise like that. It is more like a thermal corridor, a broad range where, under the right circumstances, liquid water could exist on a suitable surface. Put a gas giant in that corridor and the phrase still technically applies to the location, even if the planet itself is nothing like Earth. Yet that does not make the location emotionally empty. A giant planet in the habitable zone still matters because it tells us the corridor is occupied. It means the region is not just a conceptual band around the star. It contains mass, history, and gravitational influence. It may contain moons. It may alter where other bodies can remain stable. It may hint at a formation story richer than we assumed. And because Alpha Centauri A is so near, those implications feel sharper than they would anywhere else. We cannot help picturing the system more concretely, not in fantasy detail, but in layout. Here is the star. Here is a broad, temperate region. Here may be a giant world glowing faintly in the mid-infrared. Here is the companion star farther out, its own presence shaping the larger architecture. Here is a relatively low level of exozodiacal dust, clearing some of the haze. Suddenly the place has parts. Once a place has parts, the imagination no longer floats freely, it starts to navigate. That is one of the quiet thresholds this story marks. We are moving from wondering whether Alpha Centauri A has planets in the abstract to wondering what kind of planetary arrangement best fits the specific evidence we now have. That may sound like a subtle shift. It is not. It is the shift from myth to cartography. And cartography always begins with imperfect lines. The earliest maps of coastlines were ragged, incomplete, full of errors and missing regions. Yet they were revolutionary because they turned unknown space into a place where better questions could be asked. Where is the harbour? How far does the river run? What lies inland? A rough map changes thought more than a perfect blank ever could. So one is something like that. A rough mark on the edge of a map, maybe real, maybe needing revision, but too specific to ignore. It tells us where to look harder. It tells us which assumptions to discard. It tells us that Alpha Centauri A is no longer just waiting to be imagined. It has entered the harder, more rewarding phase of being investigated. And once that happens, another feeling begins to build beneath the science itself. Not urgency, something steadier. The sense that while Earth moves through its ordinary nights, while people sleep, work, argue, drive home, and forget to look up, instruments are quietly testing whether the nearest sun-like star has its own hidden order of worlds. That may be the most moving part of all. Not the possibility of a giant planet by itself, and not even the technical achievement, though both are extraordinary. It is the fact that this search is happening at the scale of ordinary life, while someone makes tea in a dark kitchen, while another person falls asleep on a couch with the television still glowing, while whole cities move through weather and traffic and appointments. A telescope far from Earth is gathering faint mid-infrared light to test whether the nearest solar twin has a world we can almost, but not quite, hold in view. That contrast does something to the mind. It brings astronomy down from abstraction and sets it beside the rhythm of being human. The universe does not become smaller. Our access to it becomes more intimate. And intimacy changes the emotional texture of distance. Alpha Centauri is still unimaginably far away in practical terms. No spacecraft we have ever built comes close to making that journey plausible on a human timescale. Even the fastest things we have sent into space would need many thousands of years. So nothing in this story should be mistaken for nearness in the sense of travel. But travel is not the only measure of closeness. There is also the closeness of resolution, of repeated observation, of being able to say not just that a star exists, but that a possible giant planet may circle it at roughly this distance, at roughly this temperature, in roughly this sort of orbit, through a system that seems relatively clean of obscuring dust. That is a form of nearness our species did not possess until very recently. And it's easy to miss how radical that is, because the details arrive so quietly. A flux measurement at 15.5 microns, a projected separation of about 1.5 arcseconds, sensitivity to objects with temperatures around the freezing point of water or somewhat below, limits on EXO's zodiacal dust only a few times brighter than our own zodiacal cloud. These facts can look small on a page, but put them back into human terms and the picture changes completely. We are measuring the faint heat of a possible world around another sun. We are constraining the diffuse dust in that world's larger environment. We are testing its movement over months. We are doing this not around some distant anonymous star, but around the nearest one that resembles our own. That should feel impossible, and in one historical sense it still does. A few generations ago, it would have belonged to fiction. A few centuries ago, it would have sounded like a category mistake, the kind of thing human beings simply do not get to know. Yet here we are, not with full answers, but with enough contact for the old idea of the stars as unreachable points to start breaking down. This is why frontier science can feel so emotionally different from settled science. Settled science gives you confidence. Frontier science gives you contact. It tells you not only what is known, but where the edge of knowledge has begun to press against something real. Alpha Centauri A is now one of those edges. And once a system reaches that status, every future observation carries a little more weight, because it is no longer generic observing, it is follow-up. It is testing a possibility that already has shape, a possible orbit, a possible mass range, a possible connection to an earlier candidate, a possible system architecture beginning to emerge around the nearest solar twin. Even the dust result becomes part of that atmosphere of expectation. A system with low exozodiacal dust is not automatically easy, but it is less self-concealing. That matters enormously for the future, because one of the great obstacles in direct imaging is not just the star itself, but the background haze of a planetary system's own debris. If Alpha Centauri A is relatively clean, then the difficulty is still severe, but not hopelessly compounded. That gives future instruments and future campaigns a better chance of separating real objects from environmental clutter. In other words, the story is not narrowing, it is opening. A candidate giant planet, if confirmed, would be the nearest exoplanet orbiting in the habitable zone of a sun-like star. That sentence has to be handled carefully, because the phrasing can mislead. Again, habitable zone does not mean habitable planet, and the object indicated by S1 is likely a gas giant, not a rocky world. But even with those guardrails firmly in place, the significance remains enormous. The nearest sun-like system would not merely host planets in some broad abstract sense. It would host at least one large world in the very region people most instinctively care about when they imagine where liquid water could, under the right conditions, become possible. That matters scientifically because it constrains formation and dynamics. It matters emotionally because it changes the nearest familiar star from a symbol into a place where planetary warmth, orbital timing, and thermal detection now intersect in a physically meaningful way. There is also a deeper lesson here about how we misunderstand difficulty. Most people assume the most difficult astronomical searches involve the most distant things. And often that is true, but not always. Sometimes the hardest object to see is not the farthest one. It is the faint one next to the brightest thing in the frame. That is the real paradox of Alpha Centauri EA. Its closeness makes it special, but not simple. Nearness gives us leverage, but brightness takes it away again. The system invites comparison to home, then punishes us for trying to inspect it casually. It says, in effect, yes, I am nearby by cosmic standards. No, you do not get to know me easily. And perhaps that is part of why this story feels so strangely compelling. The nearest solar twin has not yielded to us as a gift. It has yielded as a challenge. We did not simply look at it and see worlds. We had to build instruments capable of reducing glare, sensitive to warmth, stable enough to detect faint emission, subtle enough to turn one epoch of data into a candidate worth serious attention, then even that was not enough. We had to return and fail to see it again, and then think harder about what that failure might mean. This is science at its most human, not because it is uncertain, but because it is disciplined under uncertainty, curious without being reckless, hopeful without pretending the answer is already known. The title promises shock, but the deeper truth is subtler than shock. It is consequence. The consequence of having reached a point where the nearest sun-like neighbourhood can no longer remain just a direction on a star chart. And that shift will not be reversed. Even if S1 were ultimately explained away, Alpha Centauri A would not go back to being simple. Webb has already changed that. The dust limits alone matter. The demonstrated sensitivity matters. The fact that the system can be probed this deeply matters. The threshold has been crossed. We now know what kind of questions can be asked there with real observational weight. But if S1 is real, then the threshold is even more significant. It would mean that in our own stellar neighbourhood, around the nearest star that feels remotely like the Sun, a giant world has already begun to reveal itself, not through a dramatic image or a clean cinematic discovery, but through a whisper of heat and the stubborn logic of follow-up. There is something almost perfect about that. A neighbouring system answering back not with spectacle, but with a thermal point source, a faint presence, exactly where careful looking suggested something might one day appear, then gone again. Not necessarily because it was never there, but because the orbit continued and the window closed. That image stays with you. A world not blinking in and out like a fantasy, but passing through visibility the way a real thing would. That is what gives the story its calm pull. It is not built on exaggeration. It is built on the realization that nearby reality may already be more structured than our older vision of the sky allowed us to feel. And once that realization takes hold, you begin to sense that the night above Earth is no longer a flat arrangement of stars. It is layered with neighborhoods, some cleaner than expected, some more crowded, some still hidden, each awaiting the moment when technique, timing, and patience line up just well enough for the next faint clue to appear. And once you begin thinking of the sky that way, the old emotional distance never fully returns. The stars still look quiet from Earth. They still seem fixed, serene, almost indifferent. A child can look up and see the same basic pattern that human beings saw thousands of years ago. That surface continuity is real. But beneath it, the meaning has changed. We now know that many of those points are not solitary lights. They are systems, some with tightly packed planets, some with giant worlds skimming close to their stars, some with rocky planets in extreme orbits, some with debris belts, resonances, atmospheres, weather. And somewhere among those transformed points sits Alpha Centauri A, the nearest sun-like star, perhaps no longer just a star at all in our minds, but the centre of a partly revealed planetary scene. This is why the title's promise keeps deepening instead of exhausting itself. Webb looked into Alpha Centauri. At first that sounds like a simple act of observation, but the more you unpack it, the more intimate and difficult it becomes. Webb did not glance at a bright star and happened to notice something interesting. It entered one of the most delicate contests in modern astronomy, suppressing the glare of a nearby sun in order to isolate the faint thermal presence of something that may be circling it. What it saw was not shocking because it was monstrous or exotic. It was shocking because it may have been ordinary in the most important way imaginable. A giant planet around the nearest solar twin should not be impossible. In fact, in a galaxy full of planets, it may be exactly the kind of thing we should expect. But expectation is one thing, contact is another. A world can be statistically unsurprising and still emotionally overwhelming once it becomes local enough to matter. If a giant planet really is moving through the broad temperate region around Alpha Centauri, then the nearest familiar star system is not only populated, it is populated in a way that begins to feel structurally legible. That word again, structure. Human beings are changed by structure more than by scale alone. Pure vastness can numb the mind after a while. Another immense number, another unreachable distance, another ancient galaxy. These things inspire awe, but they can also drift away from the body. Structure does the opposite. Structure pulls the universe inward. It gives you arrangement, relation, consequence. One world here, another region there, dust thin in one zone, perhaps thicker elsewhere, a possible orbit crossing a sensitivity boundary, a companion star reshaping the outskirts of the system over long spans of time. Once arrangement appears, the place stops feeling empty no matter how far away it is. That is why Alpha Centauri A has such unusual power over the imagination right now. It sits at the intersection of two different human instincts. One is the longing for a first real neighbour in the stars, a place beyond the solar system that still feels close enough to compare with home. The other is the need for honesty, for evidence, for not turning that longing into fiction just because the target is emotionally loaded. S1 holds those two instincts in tension beautifully. It invites imagination, then immediately disciplines it. It says, here is a plausible thermal source near the habitable zone of the nearest sun-like star. Here is why that matters. Here is why you must not exaggerate it. Here is why it remains alive anyway. That kind of tension is rare and valuable. It creates a form of wonder that does not depend on illusion. And it also restores something important to the idea of scientific discovery: slowness. We live in a culture that expects revelation to arrive finished. The headline lands, the answer appears, and the story is sorted into true or false before most people have even had time to feel it. But many of the deepest discoveries do not come to us in a single emotional package. They arrive in stages, first a hint, then a challenge, then a follow-up that complicates the hint rather than resolving it, then improved models, then more observations, then, sometimes years later, the shape of the truth begins to hold. Alpha Centauri A may be in one of those stages right now. That matters because it means we're not standing after the story, looking back at a polished result. We are inside it. We are living through the moment when the nearest solar twin has begun to resist blankness and acquire specific hidden possibilities. That is a different kind of privilege than certainty. A little more fragile, perhaps, a little more demanding, but also more intimate, because it lets us feel what science feels like before the edges are sanded down. And the closer the target, the more emotionally potent that can become. If this same observational pattern were unfolding around a star 200 light-years away, it would still be a real scientific event, but the emotional voltage would be lower because the star would remain outside our inner map of nearby reality. Alpha Centauri does not allow that distance of feeling. It presses closer, not physically, but psychologically. It is the star system people have imagined first for so long that any evidence of actual planetary order there immediately feels disproportionate to the data itself. That is why discipline matters so much in telling this story. The easiest thing would be to inflate it, to leap from candidate to confirmation, from gas giant to fantasy world, from one thermal signal to a whole populated system, but inflation would actually make the story smaller. It would flatten the real drama, which lies in how difficult, careful, and consequential this threshold really is. The truth is stronger. The truth is that Webb found the strongest evidence yet for a candidate giant planet around Alpha Centauri A. The truth is that the signal appeared where such an object could plausibly live, at roughly 2 astronomical units, glowing in the mid-infrared. The truth is that follow-up observations did not recover it, but those non-detections do not simply erase the candidate, because orbital motion may have carried it into a region of poor sensitivity. The truth is that the team argues against simpler explanations like background contamination or processing artifacts, while still stopping well short of claiming confirmation. The truth is that earlier hints from ground-based observations may connect to the same object, though that remains unsettled. And the truth is that Webb also placed extraordinary limits on the dust in the system, making Alpha Centauri A one of the most favourable nearby places for future direct searches. That's enough, more than enough, because once those truths are allowed to breathe, they do something remarkable. They make the nearest sun-like star feel less like a symbol of someday travel and more like a present-tense observational landscape. It becomes a place with thermal thresholds, orbital suspense, and real constraints. A place where future confirmation would not just add another exoplanet to the catalogue, but redraw the emotional boundary between our system and the next one. And that redrawing has consequences beyond Alpha Centauri itself. It changes what we mean when we talk about nearby stars. It changes how missions are designed, how future telescopes justify their sensitivity goals, how direct imaging is framed not as a niche technical exercise, but as a way of turning stellar points into environments. If we can begin to do this here, then the sky around us starts to reorganize into targets of increasing intimacy, not because they are less distant, but because they are increasingly knowable. That may be the quiet revolution under the whole story. Not that Alpha Centauri suddenly became dramatic, but that nearby reality has become observable in a new register, heat instead of glitter, motion instead of myth, constraints instead of empty yearning. The nearest solar twin no longer belongs only to novels, diagrams, and speculation. It belongs to the long, patient work of measurement. And measurement, when it is this careful, has a strange power. It can take something people have romanticized for generations and make it feel more human by making it more real. Because reality resists us. It withholds itself. It forces us to return. It gives us one point of light, then a gap, then another possibility, and asks whether we have the patience to keep looking without lying to ourselves. That is exactly the kind of relationship we are beginning to form with Alpha Centauri A. Not possession, not mastery. Recognition. The nearest familiar star is starting to answer in specifics, and once a neighbouring system begins to do that, even faintly, we are drawn toward an even deeper realization. The great barrier between stars is still there, but the barrier between stars as lights and stars as places is beginning to thin. And that thinning may be one of the most important changes in human perspective now underway, even if it arrives so quietly that most people never notice it happening. For thousands of years, stars were points first and places never, even when we learned what they physically were, even when we understood that they were suns, they remained emotionally flat at a distance. A star could be hotter, larger, older, more massive, more violent, but it was still mostly a source, light, spectrum, motion, not neighbourhood. The solar system alone had texture. It alone had named worlds, belts, atmospheres, storms, seasonal patterns, orbital drama. Everywhere else in the sky remained simplified by distance into almost pure abstraction. That simplification is starting to fail. Not all at once, not cleanly, but enough that we can feel the old mental model weakening. The nearest stars are no longer guaranteed to stay featureless. They can begin to acquire interiors in the imagination because observation now gives us permission to think of them that way. Not as fantasies we project onto the dark, but as systems under investigation. That is what Alpha Centauri A represents so strongly in this moment. It is not merely a bright point with prestige. It is a test case for whether the nearest solar twin can be made to yield its hidden planetary arrangement through patience, wavelength choice, and ever more disciplined control of starlight. That is why the image of S1 matters so much even though it is only a point. It acts like a breach in the old wall, a tiny breach, uncertain, still contested, but enough to let structure into view. And structure changes everything. Once structure appears, your mind starts asking different questions. Not, is there something there in the vaguest possible way, but what kind of system would produce this? If there is a giant planet at roughly 2 astronomical units, how did it form in a binary system? How stable is the orbit over long spans? Could there be inner rocky planets still hidden from us? Could moons orbit the giant world? How does the relatively faint exozodiacal dust fit with the system's formation history? Is the apparent cleanliness of the dust a sign of dynamical sculpting, of efficient clearing, of an older mature architecture? These are richer questions than fantasy ever produces, because they are limited by reality instead of inflated by desire. And reality has a way of becoming more absorbing the more specific it gets. We often assume that uncertainty weakens a story. In shallow storytelling it does, but in real science, uncertainty often makes a story stronger because it keeps the object alive in time. A fully solved result sits in the archive. A partly resolved result moves forward. It creates anticipation, model testing, return visits, revised understanding. Alpha Centauri A has now entered that state. It is no longer just a bright known star. It is a site of unfinished observation. That matters because unfinished observation creates a future. There will be more attempts, more careful timing, more efforts to catch the system when a candidate world, if real, moves back into a region of better visibility. More pressure on the orbital models, more scrutiny of whether S1 and C1 can be reconciled as one body instead of two unrelated hints. More work on understanding exactly how clean the surrounding environment is and what that means for future direct imaging. So the emotional force of this story is not only in what happened in August of 2024, it is also in what the event set in motion. That is easy to overlook because we are so trained to treat scientific moments as endpoints. But many of the most consequential observations are really beginnings in disguise. One point source appears, and suddenly a whole program of thought reorganizes itself around it. Resources shift, priorities sharpen. The next question becomes more specific. The future becomes less generic. Alpha Centauri A has become less generic. That may sound like a small thing. It is not. Generic stars remain interchangeable in the public imagination. Famous stars are remembered, but only a few stars become locally meaningful in a scientific sense. Places where people begin to talk about system architecture rather than mere stellar identity. Our own sun, of course, Proxima Centauri now, because it has confirmed planets, and one of them sits in a region people instinctively care about. And Alpha Centauri A may be joining that group in a much more emotionally charged way, because it resembles the sun more closely, and therefore invites a sharper kind of comparison. Comparison is powerful, but it is also dangerous. It can make us rush. It can make us want Alpha Centauri A to become a second solar system simply because the idea is irresistible. The discipline of this story lies in resisting that temptation. We do not need a second solar system for the story to matter. We do not need an Earth twin. We do not need life. We do not even need final confirmation yet. What we already have is enough to alter perspective. The nearest sun-like star may host a giant planet in a broad temperate region, and the evidence is strong enough that serious observers cannot treat the system as blank anymore. That alone is transformative. It transforms not by offering a fantasy ending, but by narrowing the gap between home and elsewhere, until recently. Elsewhere began far beyond any system we could emotionally map. Now elsewhere may begin with the very next sun-like household. And that phrase, household, is useful here, not because it romanticizes the system, but because it conveys arrangement. A household has rooms, corners, pathways, places where things collect and places they do not. A planetary system is not a random scattering. It has zones shaped by heat, gravity, collisions, time. If Alpha Centauri A hosts a giant planet around 2 astronomical units and relatively little dust in the relevant regions, then its household may be cleaner, more orderly, or at least differently organized than we once assumed. Again, we must be careful. Cleaner in dust does not mean simple. A low exozodiacal glow is not a full portrait. It is one clue, but clues like that matter, because they tell us the system is not burying all its secrets under luminous clutter. Some of its architecture may truly be accessible if we are patient enough. And patience is one of the hidden themes in this whole story. Not patience as passive waiting, patience as a method. The willingness to accept that one of the nearest and most emotionally charged targets in astronomy will reveal itself on its own terms or not at all. The willingness to sit inside ambiguity without either exaggerating or losing interest. The willingness to let follow-up non-detections remain meaningful instead of treating them as narrative failure. That kind of patience is rare outside science, and maybe rare inside it too, but it is exactly what the sky demands when the object of interest is both nearby and almost impossible to isolate. There is also something humbling in the fact that the barrier here is not mainly distance but brilliance. Alpha Centauri A is hard because it shines too well. That should stay with us. The nearest solar twin is not hidden behind remoteness alone. It is hidden behind its own radiance. A star can conceal its worlds by being exactly what it is, a star. So Webb's achievement is not only that it saw a possible planet, it is that it entered the flood of starlight and made room, however briefly, for something fainter to count as real. That is a profound shift in human seeing. And once it happens, even tentatively, you start to understand that the future of astronomy will not only be about looking deeper into the universe, it will also be about looking more delicately into nearby systems until stars we have long treated as simple lights begin to develop the textures of places. Until recently, that idea would have sounded almost too refined to matter outside the field. Looking more delicately does not sound like a revolution. It sounds like a technical adjustment. But many revolutions in knowledge begin that way, not with a louder question, but with a quieter instrument, not with a grander theory, but with a more careful refusal to let the obvious thing dominate the frame. That is what happened here. Webb looked at a star people thought they already understood and asked a different question. Not what Alpha Centauri A is, we knew that. Not whether it shines. Of course it does. The deeper question was whether its brightness had been hiding a local reality all along, whether the nearest sun-like star might already contain the sort of planetary arrangement we have dreamed about, modelled and searched for, but never cleanly held in view. And the answer, at least for now, is not yes in the final sense. The answer is something almost more powerful. Maybe, seriously maybe, that phrase can sound weak in ordinary conversation. In frontier observation, it can be momentous. A serious maybe means the evidence has crossed a threshold. It means the signal is not just wishful thinking. It means plausible alternatives have been tested and did not immediately dissolve the event. It means further observation is not an act of blind hope, but of focused investigation. That is where S1 lives. A serious maybe around the nearest solar twin. And because the system is so emotionally charged, the temptation is always to jump ahead, to imagine oceans on unseen moons, to turn the habitable zone into an invitation rather than a temperature band, to let proximity inflate possibility into certainty. But the real discipline of this story is that it does not need those shortcuts. A giant planet candidate is enough. A warm object orbiting in the broad temperate region around Alpha Centauri A is enough. The fact that its possible presence had to be extracted through coronagraphic struggle and infrared sensitivity is enough. The fact that it appeared, then disappeared in a way that may fit orbital motion, is enough. Because enough has changed already. The nearest sun-like star is no longer simply the place we might go someday. In human imagination, it has started to become the place we are learning now. That is a much stranger category. It belongs neither to fiction nor to completion. It belongs to active reality, to a place that is still far beyond reach and yet already entering the sphere of measured knowledge. That shift affects the meaning of patience in a deeper way. When we think about waiting in science, we often imagine delay as an inconvenience, the time between one answer and the next. But with Alpha Centauri A, waiting is part of what gives the story its shape. The candidate may need time to move. The next favourable viewing angle may arrive months or years later. The system's truth may emerge not in a burst but in recurrence. A point source appears once. Models tighten. Future observations aim at predicted windows. If the world is real, it comes back into legibility. If not, the absence itself begins to tell a more precise story. That is not frustrating in the deepest sense. It is intimate. It means the system is no longer responding only to our curiosity. We are responding to its rhythms. There is something almost profound in that reversal. For so long, stars were passive objects in human thought. We looked, measured, named, classified. But when you begin searching for faint worlds next to bright stars, the relationship becomes more reciprocal, not because the star chooses, but because the geometry does. Reality sets the schedule. The system reveals itself when motion, contrast, and instrument sensitivity briefly align. We do not command the answer, we meet it. That is one reason this story feels so calm, even at its most exciting. It is not built on conquest. It is built on encounter. And encounters are often remembered less for the volume of what happened than for the fact that something once distant became specific. That is what S1 has done, confirmed or not. It has made Alpha Centauri specific. Before this, the star could still function mostly as a symbol. Nearest solar twin, bright southern beacon, classic destination of speculative future travel. After this, it is harder to hold it that way. Now there is a candidate point source at roughly 2 astronomical units in the mind, a possible giant planet, a relatively clean dust environment, a question of whether an earlier infrared hint from another instrument may connect to the same orbit. The system has begun accumulating particulars, And particulars change emotional reality faster than scale ever does. Think about how little it takes to transform a place in ordinary life. A house is just a house until you know someone lives there. A street is just a street until you know where it leads. A shoreline is just a line until someone marks a harbour on it. After that, the place is altered forever in the imagination. It has acquired an inside. Alpha Centauri A is acquiring an inside. Not fully, not even close, but enough to matter. And that matters far beyond one candidate planet, because it hints at the direction astronomy is moving as a whole. We're entering an era in which nearby stars will not remain emotionally flat for much longer. Direct imaging, thermal sensitivity, ever better starlight suppression, future large telescopes on the ground and in space. All of these point toward a sky that will gradually become populated not just with known planets and catalogues, but with locally meaningful systems that we can compare, revisit, map in stages, and eventually maybe characterize in ways that today still sound almost unreal. Alpha Centauri A is one of the first places where that future stops sounding abstract. That is why the dust results should stay in the story as more than a technical side note. It is easy to let all the emotional energy collect around the candidate signal itself, but the faintness of the exozodiacal dust is part of the same transformation. It tells us that the system may be more transparent to future searches than feared. The room, to return to that image, may contain less glowing haze than expected. If you are trying to see a warm body move near a bright source that matters enormously, it means each future attempt begins from a cleaner observational floor. The star is still hard, the contrast is still brutal, but the system does not seem determined to hide everything behind its own debris. So what Webb may have done is larger than finding one possible world. It may have identified one of the most promising nearby arenas in which repeated direct searches can genuinely reshape our sense of local cosmic geography. That phrase sounds grand, but the reality underneath it is very simple. We may be starting to map the next stellar household over, not in the childish sense of drawing continents where none are known, in the adult sense, the measured sense, the sense of saying, here is the star, here is a broad temperate region, here is a possible giant planet, here is a dust level, here is a likely blind spot, here is when to look again. That is cartography at the edge of possibility. And it is impossible to hold that thought for long without feeling something change in your relationship to the night sky. Because a mapped household is different from a romantic destination. A destination belongs to longing, a household belongs to reality. It may still be unreachable, but it's no longer vague. That is the emotional direction this story keeps moving toward. Not bigger numbers, not louder wonder, nearer meaning. The nearest sun-like star is becoming less symbolic and more inhabited by facts. And facts, when they gather around a place that close, can do something fiction alone never could. They can make the place feel present. Present not in the room with us, of course. Present in thought, present in attention, present in the slow reorganization of what counts as our local universe. And once a neighbouring star enters that category, the next thing you feel is not triumph. It's a kind of calm astonishment at how recently all of this would have been impossible, and how normal it may someday become. And that sense of someday this will feel normal is quietly one of the most disorienting parts of the entire story. Because right now, it still feels rare, fragile, almost accidental, a single candidate signal, one system pushed to the limits of what we can do, a handful of observations carefully interpreted, debated, revisited. It feels like standing at the very edge of capability, where everything could still fall back into uncertainty if we are not careful. But if you widen the frame just slightly, you begin to see a different pattern forming. This is how it always starts. At first, a technique is new and delicate. It works only in the best conditions, on the most favourable targets, with results that demand caution. Then, slowly, the method stabilizes, instruments improve, data processing becomes more refined, the community learns what is real and what is misleading, and what once felt exceptional begins to repeat. Direct imaging is following that path. For a long time, directly seeing planets was almost impossible except for very large, very young, very hot worlds far from their stars, bright giants glowing from leftover heat, easy to separate from the star simply because they were distant enough. That was the early phase, useful, but limited. It told us such planets exist, but it did not touch the kind of systems people instinctively compare to our own. What Webb is doing around Alpha Centauri A belongs to a later phase. Closer in, cooler, more subtle, more demanding. Not young blazing giants, but temperate objects radiating faint heat. Not wide separations, but regions closer to the star where habitability questions begin to live. Not distant anonymous systems, but the nearest sun-like star itself. That is a different level of intimacy. And once that level becomes possible, even in a fragile way, it does not remain isolated. It spreads. Other nearby stars become candidates for similar treatment. Future instruments are designed with these exact challenges in mind. Coronagraphs become more precise. Data reduction becomes more disciplined. Observing strategies become more strategic, timed not just for convenience but for orbital prediction. So Alpha Centauri A is not just a story about one system. It is a preview of what nearby space will start to feel like when enough of these efforts accumulate. A sky where certain stars are no longer just points, or even just hosts of statistically inferred planets, but places where we have partial maps, where we know where something might be, when it might appear, how bright it might glow, and how the system around it behaves. That is a profound shift in how knowledge feels. Because knowledge is not only about facts, it is about how those facts arrange themselves into something you can revisit, something you can return to with new questions, something that does not reset to zero every time you think about it. Alpha Centauri A has become revisitable. That may be the simplest way to say it. You can now think about that system not as a blank, but as a place with an ongoing story, a story with a past observation, a present uncertainty, and a future set of tests. That alone is enough to anchor attention in a way that distant discoveries rarely do. And it also creates a different kind of emotional continuity. Instead of a single moment of discovery followed by closure, you get a thread. August 2024 becomes a reference point. Early 2025 becomes another. The next observation, whenever it happens, will not be isolated. It will connect backward and forward. It will either strengthen the idea of a moving world or force a rethinking of everything that came before. That continuity is what turns astronomy from a collection of facts into a lived process. And the closer the system, the more that process feels personal. Not because we are involved in a direct way, but because the distance is small enough, in cosmic terms, that the mind refuses to keep it abstract. You begin to imagine the system in motion, not vividly, not with invented detail, but with enough structure that it feels like something unfolding rather than something static. A giant planet, if it exists, tracing an orbit every few years. A region where it becomes visible, then invisible again. A companion star shaping the wider environment over decades. A relatively clean field of dust allowing clearer glimpses when conditions align. These are not just data points anymore, they are behaviours. And behaviour is what makes something feel real. You can see this even in how the disappearance of S1 changes tone. If the signal had simply remained visible, stable, unchanged, the story would be simpler, easier to tell, easier to believe, but perhaps also less alive. The disappearance forces us to think dynamically. It forces us to consider motion, timing, sensitivity, geometry. It turns a static detection into a system in motion. In a strange way, the absence deepens the presence, because it suggests the object is not an artifact frozen in one image, but something participating in a physical story that continues whether we see it or not. That is one of the quiet lessons of astronomy that only becomes clear at this level of detail. Reality does not arrange itself for our convenience. Objects do not stay where we can easily observe them. The universe is always moving, always evolving, always shifting relative to our line of sight. The act of seeing is always partial, always timed, always dependent on conditions. And yet, despite all of that, we are beginning to succeed. That success is not absolute, it is not clean, it is not final, but it is enough. Enough to say that the nearest solar twin is no longer beyond the reach of direct investigation. Enough to say that we can detect the faint thermal signature of a possible world there. Enough to say that we can constrain the environment around it. Enough to say that we can return and test whether the system behaves the way our models predict. That is a threshold worth pausing on, because once a threshold like that is crossed, it tends not to close again. Even if S1 were eventually explained away, the capability remains, the method remains, the understanding of how to push further remains. The next attempt will not start from ignorance. It will start from everything we have learned here. So Alpha Centauri A becomes a kind of anchor point for the future. Not the final answer, the first difficult answer, and that distinction matters, because first answers are rarely the most dramatic ones. They are the ones that open the door, the ones that prove a question can be asked in a meaningful way, the ones that show the universe is not withholding everything at that scale, only demanding that we learn how to look properly. That is exactly what Webb has done. It has shown that even in the harshest conditions, bright star, close separation, faint target, it is possible to extract something that behaves like a planetary candidate around the nearest sun-like star. And once you understand that, the sky shifts again, almost imperceptibly, because now Alpha Centauri A is not just a place we have begun to map. It is a place we expect to map further. An expectation, when it is grounded in real observation, is one of the most powerful forces in science. It pulls attention forward, it organizes effort, it turns curiosity into trajectory, which means this story is not ending with what Webb saw. It is extending into what we will see next. And what we will see next will not arrive as a surprise in the old sense. It will arrive as a return. That is the quiet transformation that has already taken place. Alpha Centauri. A is no longer just something we point at. It is something we come back to with intention. The difference seems small, but it changes everything about how the story unfolds. A first look is exploration, a second look is testing, a third look becomes expectation, and somewhere along that sequence, a distant star system becomes a place where patterns begin to emerge. If S1 is real, then its absence in early 2025 is not an ending. It is a coordinate, a constraint on where it might have moved, how fast, and into which region of the instrument's blind structure it may have passed. That transforms the next observation from a general search into a targeted one. We are no longer asking, is there something there? We are asking, if it is there, where should it reappear? That is a different level of engagement. And it is one of the reasons this story carries such a calm, persistent pull rather than a single spike of excitement. Because the real payoff is not in one moment. It is in the continuity of attention that follows. Imagine watching a distant shoreline through shifting fog. At first, you see nothing. Then for a brief moment, a structure appears, a shape, a tower, something that clearly belongs to land. Then the fog closes again. You do not conclude that the land vanished. You begin to understand the rhythm of the fog. You begin to predict when it might open again, where your view might be clearer, how to position yourself to catch the next glimpse. That is what we are doing with Alpha Centauri A. The fog is not literal. It is the combination of glare, sensitivity limits, and orbital motion, but the effect is similar. Visibility is intermittent, and meaning accumulates across those intervals. This is also where the broader implications begin to settle in more fully. Because if a giant planet truly occupies that region around Alpha Centauri A, then the nearest solar twin is not just populated, it is dynamically alive in a way that mirrors the kind of complexity we see in our own system. Not identical complexity, not a mirror image, but enough to say that planetary architecture is not something that begins far away. It begins here, at the smallest cosmic distance that still separates one star system from another. That has a subtle but lasting effect on how we think about elsewhere. Elsewhere used to begin at a kind of emotional infinity. It was always distant enough to feel abstract. Now elsewhere may begin just beyond the edge of our own system, at a distance that is still vast but no longer empty of detail. The nearest sun-like star is no longer a placeholder. It is a site of investigation with emerging structure. And that makes the universe feel denser in the most meaningful way. Not denser in matter, but denser in knowable places. Because once one nearby system begins to yield, others follow, not immediately, not effortlessly, but inevitably. The techniques improve, the targets expand, the questions sharpen. What we learn from Alpha Centauri A will feed directly into how we approach the next nearest sun-like stars, the next systems where glare must be suppressed, where thermal emission must be isolated, where orbital timing must be respected. This is how a field grows, not by a single dramatic breakthrough, but by a chain of increasingly precise attempts that begin to overlap and reinforce each other. And at the centre of that chain, Alpha Centauri A will remain a reference point. The nearest case, the most emotionally charged test, the place where we first learned how difficult and how possible it is to directly probe the architecture of a solar twin so close to us. There's also a deeper shift happening in how we relate to uncertainty itself. In many areas of life, uncertainty is something to eliminate as quickly as possible. It is uncomfortable, inconvenient, something to resolve. But in this kind of science, uncertainty becomes a space to inhabit productively. Not vague uncertainty, but structured uncertainty. The kind where each unknown is framed by what we do know. The kind where absence carries information, where timing carries information, where even the failure to detect something under certain conditions becomes part of the map, as one exists inside that space. It is not a confirmed planet. It is not a dismissed artifact. It is a candidate whose behaviour must be tested across time, whose properties must be constrained through repeated effort, whose reality depends on whether it can reappear in a way that matches the physics we expect. That is a demanding kind of truth. But it is also a durable one, because if the candidate holds up under that pressure, if it returns, if its orbit begins to take shape in the data, then what we will have is not just a detection. We will have a story of motion, consistency, and presence built across years. And if it does not hold up, if future observations fail to recover it even under favourable conditions, then the system will still have taught us something precise. The limits will tighten, the models will adjust, the search will refine. Either way, Alpha Centauri remains active. It does not go back to being simple. And that may be the most important point to carry forward into the final movement of this story. Because the shock in the title is not meant to leave us with a single image. It is meant to change how we see everything that follows. The fact that Webb may have glimpsed a giant world around the nearest sun-like star is not just a moment. It is a shift in baseline, a new starting point for how we think about nearby space. From now on, when you hear Alpha Centauri, it will be harder to picture only a bright point. There will be an echo of structure behind it, a possible orbit, a region at about 2 astronomical units, a faint warmth in the mid-infrared, a clean environment where future searches might succeed, a system that does not fully reveal itself, but no longer fully hides. And that echo will not fade easily. Because once a place begins to answer back, even in fragments, it becomes part of the living map of reality. And once something enters that living map, it does not need to be fully known to matter. It only needs to be real enough that we can return to it. That is where Alpha Centauri A now rests in our understanding. Not solved, not fully revealed, but no longer distant in the way it used to be. It has crossed a quiet boundary. The boundary between being something we imagine and something we can begin to track. A faint point of heat in August 2024. A silence in early 2025 that may not be absence but motion. A system that appears cleaner than expected, offering fewer obstacles than we feared. A star that looks like the sun, but refuses to give up its surroundings easily. These are not final answers, they are coordinates. And coordinates are how reality becomes navigable. If you step back now, slowly, the entire story settles into a different kind of shape. Not a dramatic arc with a sharp peak, but something more like a long, steady widening of perspective. We began with familiarity, the nearest famous star system, a name people carry almost casually. Then that familiarity was unsettled. Distance did not make the system easy. Brightness made it harder. Geometry made it elusive. The very closeness that made Alpha Centauri feel accessible turned out to be part of what hides it. Then came the shift. Webb did not simplify the system. It deepened it. It found a way to quiet the star just enough to let something else emerge. Briefly, delicately, at a distance where a giant world could plausibly exist. That emergence did not resolve the story. It complicated it in exactly the right way. The signal appeared, then slipped away, not into nothing, but into uncertainty shaped by motion, by blind spots, by the limits of our view. And from that point on, Alpha Centauri A stopped being quiet. Not loud, it's not obvious, but active. A place where we now expect behaviour. A place where the next observation matters because it connects to the last. A place where even absence carries meaning. That is the transformation, and it changes something deeper than knowledge. It changes feeling. Because the night sky you look at from Earth is no longer composed of distant lights alone. It contains places that have begun to respond to us. Not intentionally, not in any human sense, but through the steady exchange between observation and reality. We look, and something appears. We look again, and it does not. We refine, return, predict, and wait for the next alignment. It becomes a relationship of attention. And attention, when it is sustained like this, creates a kind of presence. So now, when you think about Alpha Centauri, it is harder to hold it as a simple destination. It is no longer just the star we might go to someday. It is the system we are already learning, slowly, imperfectly, but genuinely. You can imagine it more precisely now. A sun-like star casting steady light. A broad temperate region where a giant planet may be tracing an orbit of a few years. A companion star moving on a longer cycle, shaping the wider structure. A relatively thin veil of dust, allowing clearer views than expected. A faint thermal glow that appeared once, exactly where it might have been waiting, then moved beyond our reach for now. And somewhere in that arrangement, motion continues whether we are watching or not. That is perhaps the most grounding part of the story. The system does not depend on us to exist. It does not wait for confirmation. It does not pause between observations. The possible world around Alpha Centauri A, if it is real, is moving right now, completing its orbit, passing through regions we cannot see, then eventually perhaps, returning to a position where we can. And when it does, the moment will not feel like a sudden miracle. It will feel like recognition, like seeing something again that you were not certain you had truly seen before, and that is a very human kind of experience. Not overwhelming, not explosive, quietly undeniable. That is the tone this story leaves behind. Not certainty, but closeness. Not spectacle, but contact. Not an ending, but the beginning of a new way of seeing nearby space. Because the real shock was never that the universe revealed something impossible. It was that, from almost next door, it may have whispered something real, and for the first time, we were able to hear it. And once you've heard even a whisper like that, the night sky is never entirely silent again.